Hello, I'm Fergus Shanahan, and I'm here at APC Microbiome Ireland, which is housed in University College Cork in Ireland. It's a research centre that has been going now for over 20 years, funded by Science Foundation Ireland and dedicated to host microbe interactions, primarily in the gut, but elsewhere. This series of interviews will be with leading investigators in APC Microbiome Ireland, and we will begin with the director of APC, Professor Paul Ross. And Paul's interests are in the area of antimicrobial resistance.
Antimicrobial resistance, Fergus, is the process by which bacteria become resistant to antibiotics in particular, but other antimicrobial compounds as well. These are organisms that previously were sensitive, but have, by various different mechanisms, now become resistant. And so what it means in effect is that those antibiotics, those antimicrobials, are no longer effective in controlling that bacterium. Yes, it's a subset of the overall problem. So we use antimicrobials we use cleansers, different chemicals for killing bacteria. And so antibiotics are simply a subset of general antimicrobials, and bacteria, through their very, very fast evolution, can become resistant to them very fast. Viruses as such, they're not free living. They're parasites of other organisms. But viruses themselves can disseminate antibiotic resistance by picking up DNA and then infecting another cell and giving it to another cell, another bacterium. No, so the antibiotics have been exploited basically to kill bacteria. And the bacteria becoming resistant to them. So it's actually the bacteria that are becoming resistant. They can then cause an infection. And treatment of that infection with antibiotics won't be effective anymore because the bacteria themselves are resistant. It's the organisms that are becoming resistant, and that's allowing them then to cause problems with infection. We're hearing about it so much now because it's not essentially new. Bacteria have evolved mechanisms to become resistant to antibiotics, in the last century. It's becoming a big problem because of our overuse of antimicrobials. And so overuse of antibiotics, particularly it was estimated that about 80% of antibiotic use in the United States was for animal applications, particularly animal feed. And so they're feeding antibiotics as growth promoters. And that's disseminate, and so the bacteria are becoming resistant to this due to overuse. And now, unfortunately, we're reaping those problems now, in that a lot of these bacteria are becoming resistant. Yes, exactly. For instance, when you get a viral infection, very commonly people go to the doctor and they ask for antibiotics, but antibiotics you can't treat viral infections with antibiotics. You may get a bacterial infection afterwards and to clear that up, but as such, the antibiotic itself will be useless against viruses. It is a big problem. And what you're finding now is a lot of retailers, say in the States, want organic, non-antibiotic treated livestock and so on. And so we are getting it out of the system. However, some of the damage is already done. And the problem is, you might say that some of the antibiotics that are used in animals are not used in humans, which is the case. However, you get what we call multiple drug resistance. And that is that what can happen is that bacteria can genetically link a whole range of resistances together. And then they'll move them between one organism and another. And what you find is that these organisms become multiple drug resistant. I'll give you a very good example. We have a project at the moment where we looked at babies who were being given after 4 days after birth, were being given gentamicin and penicillin. And what we looked for was gentamicin and penicillin resistance in those babies. However, when we looked at those babies afterwards, what we found is that we had selected for a population of bacteria that were gent and pen resistant, but had also accumulated a whole range of resistances that were linked to those resistances. And this is what we call the resistome. And the resistome in these babies was amplified to the point where if you were to treat those babies with some other antibiotics later that they hadn't been exposed to, they may well not work for them. Yes, absolutely. And so it can horizontally transfer between individuals, and they'll carry the resistances with them. And they may even transfer those resistances to some resident bacteria that, say, would be in our own gut. Absolutely. And say there is a particular organism called vancomycin resistant enterococci. And these, at the moment, in a lot of hospitals, they're screening for carriage. So these people are not infected don't have an active infection with the organism, but they simply carry the organism in their gut, with the potential not just for that to get an infection from it, but also to transfer it to other people. And what hospitals are now doing is they're screening for that organism, and they're on the basis that if these people are at risk, then what they'll do is they'll segregate them away from other people so that they can't horizontally transfer that resistance. You mentioned about the WHO, highlighting the problem that we're facing with this. And the WHO themselves say if this goes unmanaged, untreated, we'll have about 10 million deaths a year from antimicrobial resistance. The part of the problem is that the drug companies themselves, they simply, the new antibiotics that are coming online are simply modifications of ones that are already there. And they're usually inter-kingdom ones. What I mean by that is they may be, like with Fleming, they may be moles that are killing bacteria. And for that reason, they can be very, very broad. And what you do when you take an antibiotic such as, say, ampicillin or gentamicin, you wipe out a lot of very, very good bacteria in your intestine. And you're leaving yourself open to that kind of denuded microbiome to new infections, such as with Clostridium difficile, which can be fatal in elderly people. Well, I would say, try to limit your use of antibiotics in everyday use. Like especially for preventative reasons, like you hear people with, say, acne or skin infections taking antibiotics, or people with mild colds and things like that going to the doctor to get an antibiotic. I think the onus is on each individual to limit the amount of antibiotics that you take. I suppose to set the record straight, the discovery of antibiotics in the 30s, in the 1930s, was probably the single most effective drugs that were ever identified in human medicine. It is estimated that at that time, that single invention extended the lifespan of humans by 8 years. Imagine a drug that of everyone, the average lifespan of individuals was extended by 8 years, and they still are hugely effective. Well, what you're trying to do is you're trying to avoid resistance development. And like one of the things that we're doing is we're taking advantage of, probably the best way to kill bacteria is with other bacteria. And in our gut, we carry a lot. One of the main things, like you think of bacteria in your gut and they're all eating together, and they're having a nice meal together. In our group, we don't think like that. We think of basically bacterial warfare in the gut. A lot of bacteria in the gut have developed systems where they can outcompete other bacteria that are similar to them. So, and what we can do is we can exploit these systems. A lot of these antimicrobials are called bacteriocins. They're small proteins, very in a lot of cases very difficult to get resistance to, and we haven't, humankind hasn't really exploited these to their full potential. And one very nice thing about them is they can be extremely specific. Antibiotics cause huge collateral damage on microbiomes, where these can be very, very specific and target the particular pathogen that you want without causing that huge collateral damage to your microbiome. Exactly. And so what we do is we target a particular organism, such as MRSA. People will know methicillin-resistant Staphylococcus aureus, which causes a lot of problems on the skin. So what we do is we look for bacteriocins which kill that, but don't are gentle on the other organisms that inhabit your skin that you don't particularly want to kill. Yes. So the solution may be right under our nose, literally. We each may have our own solution to some of the problems that we have with infection. Oh, I'm very optimistic. I think it's an area that we are just starting to understand. As a microbiologist, I would say microbiology as a discipline it was a kind of an oversimplification, where in microbiology we studied single isolated organisms. But microorganisms, bacteria, don't live like that. They live in very large communities. And those large communities are highly complex. A lot of these bacteria, we're finding we couldn't and still can't cultivate because they're used to living together. And they're like a separate organ in our body. And within that complexity lies a lot of the problems with bacteria that we have with respect to things like infection.